So this talk is about this project that I've been working on for the past couple of years called Project GaitNet. At this juncture, I guess some of you might do the eye roll and think that this is ImageNet for X. And to those, I say yes. It's basically the equivalent of the ImageNet for gait, that is basically human bipedal motion, the way that you walk. So this talk is split into 5 subsections. I'll give a basic introduction about the history of human gait analysis, how is it we model human kinematics involve walking actions, and then I'll cover a brief history about identifying humans by the way that you walk. The third section has, I'll kind of do a deep dive into the specifics of the data set that we have built. This happens to be the first ever planet-sized data set ever concocted. The fourth section, we'll kind of cover some basics of these idiosyncratic challenges that emerges in the domain of gait classification that you might not find in other realms of machine learning. And then we'll talk about the potential of this specific data set across different modalities of human application. So the year is 1976. A group of paleoanthropologists led by Mary Leakey, they basically make a very intriguing discovery in what is today called as Site G in a town called Laetoli in Tanzania. And what they discover is basically the stretch of hardened volcanic ash, and they discover 70 footprints, 88 foot long, which is eventually mapped to 3 different hominins. Now, what is the connection of this specific discovery in 1976 to this talk? This is the first ever proof of human bipedal gait, that is the ability of humans through our evolution to be able to walk on our 2 feet. So it's mapped to 3 hominins. The subjects are called G1, G2, G3. It's probably parents and a kid following behind them. This happens roughly about 3.5 million years ago. So if you have time this evening, go to Cal Academy of Sciences, not too far away from here. You will find this very interesting exhibit called Project GaitNet Odyssey, where you will see a whole bunch of visualizations like this. This is basically a modern human walking side by side Lucy, which is a fully preserved specimen belonging to one of our early ancestor hominins, Australopithecus afarensis. So the TLDR version is that we've been on this planet for about 10 million years. It is in the past 3 odd million years that we have mastered the art of walking on 2 feet. And this talk is going to be about analyzing how we walk and can we basically kind of build an ImageNet for the walking activity. So in this visualization, you will get to see the first time I saw this was kind of startling to me in the sense that more than 20 muscle groups are involved every time you take a single step, and including shock absorber muscles, foot lift-offs, accelerators, and so on and so forth. Here you will get to see a visualization of me, and as I take these 2 steps, what you might not realize is that there is a complicated set of harmonic interactions between your musculature and your skeletal system, and you'll get to see a very rich variation of your leg muscle engagement as well. Believe it or not, there are entire research centers dedicated towards understanding human gait, the way that you walk, the coupling between your lower body and the upper body. In fact, the time span in which I take 2 steps is typically split into 8 subphases. 2 large phases called stance phase, followed by the swing phase. And in each of these specific subphases of you taking these 2 steps, you basically have your muscular idiosyncrasies that can be harnessed as a soft biometric. So identifying humans by gait, this might seem like a sci-fi kind of a deal, but it does have a pretty interesting and checkered history. Here, I don't know how many of you are fans of Shakespeare, but a recurring theme in many of his books, right from Julius Caesar to the Hamlet to the Tempest, what's a recurring theme? He has characters identifying each other by the uniqueness of their footsteps. In fact, the word gait appears a lot of times in his books. Fast forward to 2015, if you guys have watched this movie, Mission Impossible: Rogue Nation, you have this agent who's trying to break into this high security facility, and is able to kind of cheat all biometrics by spoofing. And the only one that he's able to, they eventually catch him by is by using gait analysis. And this is kind of intriguing that this movie was released in 2015, and this technology already exists today in deployment in 2019. So, if you were to do a literature survey of how humans have been measuring gait, it is basically through these 5 different modalities using videos. There's always the scare of, surveillance state and ideas such as like that with regards to the video modality. You have pressure sensors where you have these smart sensors that are laid out on the floor. You have the modality of audio, and I think this is something that we will kind of understand natively, because kids have the ability of recognizing their parents from a very young age, but just on the basis of their footsteps. So do pets and so on and so forth. So there's a whole bunch of work where they train classifiers to identify human beings based on the audio of the footsteps. Wi-Fi is a scary proposition. Thankfully, that requires accessing physical layer information at a specific rate that is currently not allowed as per 4G. And then the last, but the most important, in our opinion, is using accelerometers and motion sensors that is embedded within every single smartphone in your hands. So this has been kind of propelled by the revolution of the so-called MEMS sensor technology. So if you were to kind of open your smartphone, and if you were to look at what's on the motherboard of the smartphone, you'll find these set of 3 sensors: the triaxial accelerometer, magnetometer, and gyroscope. Together, they kind of measure different aspects of the motion. In fact, if you want to really understand why your smartphones are called smart, and how is it that when you kind of tilt the screen, the smartphone has kind of understood that you have tilted the screen, it is basically on the basis of very simple accelerometric measurements. And the MEMS sensors together are called as the IMU triad, or the initial measurement unit sensors. So if any of you in the crowd owns a Samsung phone, you can type in this code, and it'll give you a list of all of the sensors that's on your device. If not, these sensors are actually not that hidden. If you were to just QR code this, scan this, and then it'll take you to this off-the-shelf academic toolkit that'll basically it'll give you a nice visualization of how your sensor data actually looks like. You have complete access to the sensor data on your device. And also, please be careful the next time you install an app. If they're asking if it is like, some kind of a weather app, and they're asking for your accelerometric or sensor data, it is kind of a cause for worry, because you can kind of get a very fine-grained understanding of your musculature using that particular data. So please do be careful about that. And how do these sensors work? The idea is actually rather simple. You basically have these etched in silicon. You have fixed plates, and then you have a spring mass configuration that moves when you kind of tilt and play around with your phone. And then the change in the capacitance is basically encoded. And the change in capacitance, in fact, captures the motion. And that is how, basically, just by looking at the way that the gravity is positioned, your phone kind of understands the nature of the tilt and the attitude of the device. The gyroscopes are not too dissimilar, except for the case that you're kind of measuring the imaginary Coriolis force. And the gyroscope basically gives you the angular rate on the 3 device axes, X, Y, and Z, which is popularly called as roll, pitch, and yaw. And this is basically the visualization of my bipedal gait cycles measured using the accelerometer and the gyroscopes. And what you will get to see is this quasi-repeating periodogram. And this is not too dissimilar from like your heart rate signature. So this is basically your gait signature. You see this kind of rhythmic motion repeating. And now the question is, can you eventually harness this into kind of generating like a unique signature that can be harnessed to identify a human being uniquely. And this is basically the snapshot of one of the user's gait cycles as it appears in our data set. So how do we basically attain this specific 4x100 tensor? It's done in 3 steps. You take a whole bunch of raw accelerometric data from smartphones, from volunteers from many different countries. You basically use a segmentation algorithm, and then you basically detect heel strikes, and then you kind of slice up the raw time series data, and then you kind of concoct these n by 4x100 tensors. The 4 axis, of course, mapping to the x, y, and z axis of your device. And then you have the norm axis, which is basically the magnitude. That is square root of x squared plus y squared plus z squared. That's how you get the 4 different axes. And at the end of the day, you basically have an n by 4x100 tensor. So for example, like MNIST would be considered to be a tensor of size n by 28 by 28. So we basically did this to kind of create this ImageNet equivalent called the GaitNet dataset. And let's look into some of the specifics. So when juxtaposed with the ImageNet dataset had roughly about 1.2 million images spread across 1,000 different classes. The version 1 of our dataset also has about 1.2 odd million gait cycles coming from volunteers from 117 different countries. The dataset was collected with consent, and these were volunteers who basically used the device in the wild. So you might find some papers that have largish datasets, but do bear in mind that these are academic datasets, so they come with like the proverbial grain of salt, in the sense that the patients or the subjects are required to walk in straight lines, or typically in very constrained environments, maybe in some cases they're in fact walking on treadmills, so there's not much of a deviation of the gait cycle, whereas we really wanted to kind of represent and model human bipedal gait cycles the way that human beings walk in the wild, with the phone in the bag, the phone in the back pocket, the phone in the front pocket, the phone in the hand, running towards a Caltrain, running away from, let us say, a dog. So we wanted to basically capture human gait motion in the wild. This is basically a random sampling of the gait cycle signatures of all of the volunteers in our dataset. If you actually work with this dataset long enough, or if you worked in activity recognition using accelerometric data long enough, you can literally stare at these images and predict where the phone was. Like the frill-like thing basically comes from right front pocket. The boring sinusoidal ones comes when the phone is basically in the hand. So what are the idiosyncratic challenges that comes in gait classification that you may or may not see in the classical computer vision context? First and foremost, there is a tremendous amount of intra-class variation. So one class here is one human being behind the device. So here you get to see the visualization of how my gait cycle looks like when the phone is in the left, is in my right hand, in the left side of the screen, and how the gait cycle looks like when the phone is in my right front pocket. Using accelerometers and gyroscopes. As you can see, if I've only trained the model with the phone in my right front pocket, it's very hard for it to predict how the phone is going to be, or how the accelerometric or gyroscopic signals are going to look like when the phone is in my back pocket, for example. So this is kind of unique in the sense that typically cats tend to look like cats in vision. Of course, there is the occlusion effects and all that stuff, but here the variation is much more stark. So this is another visualization of how much my gait cycle changes through different enrollment sessions. In session 1, the phone was in my hand, and then I put it in my right front pocket. And you'll find stark gender biases as well, in the sense that men tend to put the phone in their front pockets. Women can't do that. This is actually a realization that dawned upon us after kind of we got into the specific analysis of the data science of the data set. Besides this, if I were to do a PCA or a UMAP embedding, where each dot is basically a gait cycle set, and each color represents one of the 1,000 different volunteers in the data set, you'll get to see that there is absolutely no clustering that kind of emerges on the basis of the color, in the sense that this is a highly tangled representation that we are looking at the raw accelerometric data, which is another smartish way of saying that we have a profoundly tough problem on our hands. Besides this, you also have to kind of train your model to kind of be aware of the acoustic injection attacks, in the sense that one can easily concoct attacks on the sensor data on your smartphones by just pointing an ultrasonic gun at it. And this is the idea that is used to kind of take down drones, for example. On the right-hand side, you get to see the visualization of me playing an ultrasonic sound file using the VLC player, and it basically sends both the accelerometer and the gyroscope into haywire because of the fact that these, the perturbations coming from the ultrasonic sensor is basically setting the resonance mode in the accelerometers and the gyroscopes on the device. So even when the device is not moving, it appears as if it is because of the fact that I have an acoustic injection attack. And besides, if any of you here works on adversarial machine learning, that basically entails small changes in the input, kind of tailor-made to kind of confuse the deep learning classifier. This also extends to accelerometric data. On the left side of the screen, you'll see a little bit of noise being added to the image of a panda, and the DeepNet confidently predicts it to be a gibbon with 99.3% confidence. On the right-hand side, it's basically my right front pocket gait cycle signature, and the red signal is basically the perturbed one that is basically tailor-made to look as someone else's. You can kind of do this. This is probably the most sinister kind of machine learning attacks, and basically rearguarding your model against these was, in fact, a pretty important challenge to overcome. And last but not the least, there is a spatiotemporal aspect to it, and hence hybrid architectures have to be used. You can't just throw transformer models at it because these have to be eventually deployed on the device, and these are notoriously hard to train. So you have to make innovations both in terms of the initialization of these deep learning models as well as the architectures. So we had to come up with two out-of-the-box ideas. The first thing is when we train these models, we initialize the weights of these models using Grasmanian code books. If you are attending Europe's later this year, in December, we'll be kind of presenting both of these. And then in terms of the architectures, you cannot go with strictly CNNs or off-the-shelf models. So we had to come up with deep connectomics-inspired neural networks, which are sparse and which are easy to fine-tune. And how much was the accuracy that we hit? We hit about a 70% per walk cycle accuracy on a 1534 class problem. So what this means is that if there's a hall full of 1534 different people, just by taking 1 second of data, I can classify exactly who it came from with 70% accuracy. And with absolutely no constraint on where the device is, with absolutely no constraint as to whether the person was walking in straight lines or otherwise, you'll get to see the TSNE visualization of the 768 dimensional features, and you get to see this nice clustering. So what we really did achieve is disentanglement of gait cycle signatures. On the left-hand side of the screen, you get to see the PCA embeddings of the raw data. You see that there's absolutely no clustering on the basis of color. On the right-hand side, you get to see the TSNE visualization, where, again, each color represents a human being. And then you'll get to see the emergence. This is the first ever video that you're seeing of the human gait cycle universe, where you kind of see like the semantic space of the way that you walk that has been kind of unearthed by the deep neural network. So let's actually now focus on where are we going to apply this and what domains can it kind of charge the way that the ImageNet dataset did. So I think I'll kind of skip over the next couple of slides because people talked in detail about transfer learning, which basically entails training a model on one large data set and trying to kind of conquer different domains with small amounts of data being fine-tuned, used to fine-tune the model. So if I were to basically give you a challenge of training hot dog versus not hot dog, you won't train the model from scratch. You will basically download one of these ImageNet trained models and just fine tune the last classification layer. There's an entire body of literature that talks about the best practices to be used for basically using these ImageNet models and basically fine-tuning it for different tasks. And I think one of the talks previously also covered the Stanford CAST dataset. And also every single deep learning framework out there, be it either TensorFlow or PyTorch or MXNet, has extensive tutorials on how to basically do this. So some of the examples, some of the audacious examples that we tried out was, can we use this gait trained models to identify who the subject is when they're doing squats? So we basically hired a physiotherapist who basically had our own sensor. So what we were trying to do is transfer learn across different devices, that is smartphone to a PT measurement device, across different sensors from accelerometers to gyroscopes, across different activities from human gait to human squats. And then this is pretty much how the data set looked like. There was also different variations based on the squat form deformations. So the recipe is again straightforward. You strategically freeze a few of the layers, and then you leave the rest of the real estate of the neural network to be trainable. And then this is basically how the confusion matrix looked like. So we have kind of hit the cusp of being on the so-called AutoML phase, where you can kind of just use our pre-trained model trained on human gait and be able to kind of conquer human kinematics without having to collect a lot of data. Further applications include small cohort reuser identification, where if you have 20-odd students in a class, and with just one session of enrollment, you want to identify who the student is in the next upcoming batches. We hit like late 90s accuracy. If I'm not interested in identifying the human being behind the device, but get a fine-grained understanding of where the device is on the human body, I get a high 90s accuracy. If I want to classify human activity classification across different classes, I don't need much data, just fine-tune using our models. And now, does this mean that we are on the cusp of this era of surveillance, like what happened with video-based gait recognition, where it's now being deployed in airports in China, for example? I would rather say that much akin to the ImageNet case, where the emergence of this data set in the computer vision community and AI at large kind of was propelling force in thawing of the AI winter. We might, in fact, have this same unraveling within the domain of human kinematics modeling. So we had looking at applications across neurodegenerative disease model. I think someone talked about Alzheimer's. We can also extend it to Huntington's disease, Parkinson's. We are looking at applications in geriatric care, gait and posture analysis. The cool thing is this will enable and propel the democratization of your smartphone as a device of medical instrumentation. And this is not really sci-fi. You already have like peer-reviewed papers that talk about like Parkinson's disease modeling and tremor disease modeling using smartphones, accelerometers. You have papers on using the gyroscopes for hemiplegic gait. You have similar applications for different aspects of expressions of the Parkinson's disease. And then a timed up and go test, it's almost sort of a travesty that old people have to actually go to a hospital to kind of do all of these tests, whereas you have such a highly powerful device that is your smartphone that can kind of unravel all of these opportunities when you're in the comfort of your home. Similarly, you have a whole slew of applications within the domain of geriatric care. So basic idea is that if you look at all of these papers, what they do is they have like a bunch of 10 or 15 patients, and then they collect this small little data set. They basically throw simple machine learning classifiers like SVM at it. And the excuse that is being often touted is that we cannot afford to use deep learning models because there's not a huge amount of data, and we agree, and which is where transfer learning kind of kicks in. So we are trying to usher in an era where we basically have this massive model that's been trained on the GaitNet data set, and then we use small amounts of data to kind of fine-tune this pre-trained model and basically conquer a whole lot of problem domains within the domain of geriatric care, neurodegenerative disease modeling, as well as Parkinson's and Alzheimer's. Here are some of the reference publications that we've published in the past few months. And this is basically a GitHub repo. You can take a pic. It basically has all of the code and the data set as well to kind of, which showcases the ability of our GaitNet trained models to basically fine tune into a completely different domain. That's about that. Yeah. Thank you so very much.